Yeah, that's the book. All right. So for the first project, we have a headphone amplifier, and just as a show of hands, who's finished 302 here? All right, 411.
I'll take it.
Awesome. There you go. Okay, so yeah, this is kind of perfect for people who have taken 302, are in 411, know what thing or two, and are ready to hit it. Okay. So headphone amplifier, again, analog plug. So the idea of a headphone amplifier is that you have audio you want to get out of your computer, and so we're going to put an amplifier in between moment, which is going to let us really crank up the volume on that amplifier, on those headphones. And so, what is an amplifier? So this is the one that y'all all know. This is an op-amp, right? And if you have these assumptions, right, if your input resistance, like soft color, is large, and your output resistance is small, and you have this huge gain here between these two terminals, then you can do all kinds of crazy circuits to get the gain you want. So let's look at one of those. This is the non-inverting amplifier for your class. I have the analysis here, but anyway, you end up with something that looks like this. So the gain of this amplifier is positive for one thing. That's the big thing. That's why it's called non-inverting. And it's 1 plus this ratio of resistors. And then there's also the inverting amplifier. And so it's kind of turning it, the resistors are now in series with your input rather than the other branch. And then you have the analysis here again. So if you want to learn more about op-amps, or if you're a professor of that, then here's an article as well. Now, what does an op-amp really look like? So people like Texas Instruments make op-amps, and you can find them on websites like Mouser. So this is the one that's the focus of this talk today. This is the LN358. What's funny is I couldn't find out when they first started making this, but it was before 1971 was the earliest design I found of it. And so this is an old guy, but they still make thousands of them, right? So a good design can last forever. And you'll see here that if we buy 100 of them, well, that's a few people are interested, you know, then they're 47 cents a piece. So not putting them there, you know. What's inside though? So inside every amplifier is transistors. So that's how all electronic circuits work, is that they're actually transistors that make up those designs. So really there's resistors, capacitors, and inductors. Those are your electric elements. And then there's your electronic elements, which are your things like semiconductors. And so those let you do nonlinear things to your circuits. So now voltage and current isn't just defined by proportional with a resistor, derivative with a capacitor, and you can call it derivative the other way, or you can call it integral for the inductor. So these devices let you do different things with your circuits. And so this is how you make an op-amp. So within the op-amp, there's a few stages. You have the biasing, so this is where the input goes. You have the bandwidth, which this is how, you know, many signals you can amplify. And then you have the driving. So this is how much you can push with your amplifier. And we're going to talk about these individually in the context of the circuit review. Speaking of which, is this an inverting or a non-inverting amplifier? Yeah, inverting. So what you have here is there's the op-amp that we're using, and you'll notice why there's two of them. That's because we have 2 ears. There's a left and right channel for most of them, hopefully, you know, unless you're doing stereo, which is a little bit more fancy. So from there, we have 1K, and this is actually a potentiometer. So this is a 10K potentiometer. So the highest gain is, because it's inverting, if we go back a few slides, it's just the ratio of the feedback resistor and the series resistor. So in this case, the gain can be as much as 10, and that's pretty large for an amplifier because your headphone jack can actually put out a large amount of voltage, so around 3 volts peak to peak. And so this gain of 10, 30 volts, not too shabby, right? So from there, we have the audio jack itself. So how are we getting the signal from the headphones or from your computer to the headphones? This is how, right? We have a connection on the board, which is the audio jack, and then there's one that goes off the board to your headphones. So you have the ring, tip, and sleeve. So the third node here on any headphone jack will always be ground. And then it usually goes right, and then left is the tip. And so with this, you can read about more of it here. There's a lot more fancy jacks that do all types of connections. Like sometimes there's another split here, which is the microphone. And there's all types of switches people build in this kind of stuff. It gets pretty fancy pretty fast. So then let's go back to our discussion about those three things we care about. We care about the biasing, we care about the bandwidth, and we care about the driving. So for the biasing, we have what's called a capacitive coupling, or an AC coupling stage, which is just this resistor and this capacitor. And I have a little picture here, that descriptively tells you how a capacitor works, right? So as you can see, the straight line can't quite make it through the boundary, nope. But the AC makes it through. So this is what's called a high-pass filter. So the slow-moving ground can't make it through the cap, but the fast-moving signal can. And what we're going to do is we're just going to set that cutoff where it's passing at a low enough point to where all our audio signal can get through. And that's a little bit of 411 for you. But the concept is kind of true in general. Right? If you know how a circuit works, I can tell you that ground doesn't come through and the moving signal goes through, and that makes sense, right? So, oh, cool. Now, the problem is, and why we need this, is that we don't like the DC value that comes out of your audio jack over here. So what we want is we want some voltage here in order to actually have the amplifier turn on. And what we have instead is 0 volts. So the 0 volts means that the amplifier will actually turn on when the voltage is positive, and it'll amplify that part. But when it's negative, you can't see it. The amplifier is off actually. And so by having it biased at like 2.5 volts, for instance, because usually this amplifier uses 5 volts. That means that we can safely see both the high and the low voltages, which is great. So yeah, as I said, this is AC coupling, and now this amplifier can see the entire input. Now, what about the second topic, bandwidth? So bandwidth in amplifier is basically saying how fast can the amplifier see signals, right? In one way of saying it. So in another way is if the signal has a frequency, right, which is just a sine wave, right? You think of the frequency of a sine wave. Then if you don't have a resistor network, this graph from the data sheet of that amplifier is telling you that it's going to get 10,000 times bigger over here, right? And then this, is in dB scale. So every 10 represents multiplication by 10. So we have 10 dB, so it's 10 times bigger, 20 dB, 100 times bigger, 30 dB, 1,000 times bigger. And then what we're doing is we're taking this guy and we're wrapping it with our resistor divider. And that's what you see with these gain settings here and with all these graphs here. So what you see is that if the gain is set to 1, right, if we just have as much signal going out as we have going in, then our amplifier can do a lot of signals. That's what's all the way down here. So 0 dB means that it's the same amount out going in and out. There's no gain. And from there, you see that it can go all the way out here, right? So we're past almost 2 megahertz out here is the signals it can do. Now, we said that the gain of our amplifier is this red one. We're going to go to 10, a gain of 10. So that's over here. And what you see is that it has this roll-off. And what that means is that it's losing power as it goes further and further. So it's less and less gain as you try to amplify signals that are moving faster and faster. So what we really want to do is we want to amplify signals that are before this roll-off. Because this roll-off kind of tells us when our amplifier stops being an amplifier. So we want to be in this kind of range here. And what you'll notice is that human audio is 20 kilohertz. So if you look here, here's 20 kilohertz. So this is flat all the way back here. So we're great, right? We can use this amplifier. It should be okay. And yeah, that's the idea. And then as a getcha, there's another thing that kind of slows down the amplifier too, which is called the slew rate. The slew rate basically says how fast the amplifier can go from nothing to something. How fast we can go from one output to the next output. Whereas bandwidth said, okay, I have a signal and I want to respond from input to output. What's the difference between those two? So kind of the caveat is how big the signal is, right? If the signal needs to climb volts and volts, then you might be slew limited and you might be slower than you need to be. Whereas if you're bandwidth limited, then your signal could be small. And it's just going to start getting smaller and smaller, even if the slew is very sufficient. Usually you don't have to worry about this one very much. Usually this is kind of something that adds to this, but this is what's really going to tell you what your bandwidth is and how fast you can get your signals through. So how about what we're driving? How about the headphones? So here's an article that goes into detail about headphones, but by and large, headphones are 32 ohms as the lowest standard. And you want them to have flat impedance and flat phase, right? So phase means that the signal is going to be the same speed. It's going to come to the headphones, and it's going to sound like it's mixed right. If you have the right impedance, this means that the volume is going to be the same throughout the whole signal, right? So if you're going to be up here, 20 kilohertz again, then the fact that this is close to what it was at low means that the headphones are going to sound consistent from high to low frequencies. And this is just an example. This is his graph for his impedance. And so how are we going to get the signal to the headphones? So unfortunately, it turns out that the LM3508, in all its age, has not developed any better way of getting current to the output. So what we have here is that the output current for this device is limited to maybe something as low as even 5 milliamps under some conditions. And so this means is that we can't drive our 32 ohm headphones, right? We have, if you think about it, so it's the voltage at the output divided by the resistance, right? That's your current. So let's say the output is 1 volt. So 1 volt divided by 32, if it was going to get to less than 10, then it really needs to be something like 100, right? Ohms, right? So the resistance is just way too small in order for this guy to drive the headphones we want to drive. So what you see here in between is what's called a common collector. So this is a device from 438 Electronic Circuits. Great class, you can learn more about this kind of stuff. And what it does is it lowers our output resistance so that we can give power to the headphones. So one rule of thumb in headphones, or audio in general, is you want the headphones or the speakers to have about 8 times the resistance of your amplifier that's feeding them. So if you're going to have, like this graph shows, that poor LM35, he's got 300 ohms. If our headphones are only 32, then it's almost like the flip, right? We have to really lower our output resistance. And so if you do the math, this common collector lowers the output impedance to 3 ohms. So 3 ohms is less than 1/8 of 30, and so we're good. And that's kind of the basic idea. I don't have a lot of details for you here because, again, this is kind of a more advanced concept. But some of y'all are experts in this kind of stuff. It's just kind of a talk, 302 and onward, I think that you can do this, So be a little patient with your peers. So what about the other stuff, right? So how good is your amplifier? So you can usually think of your signal quality specify your impairments, the noise, and the linearity. So these two graphs, which are the power supply rejection ratio, which is basically how much your power interferes with your signal, your common mode rejection ratio, so how much the signal is rejected from other signals in the world, and then your noise, how much other stuff is added by the amplifier itself. And then your linearity basically says, if you put in a sine wave, what else is going to come out, right? If you put in a sine wave at 1 kilohertz, are you going to get a smaller sine wave at a kilohertz, and then a sine wave at 2 kilohertz, and a smaller sine wave even still at 3 kilohertz? Right? Those are what's called harmonics, right? They're multiples of the frequency on the input, and they degrade your signal quality, because you only care about the one thing at a kilohertz. Everything else is garbage. So if we use another graph from the data sheet to estimate our signal quality, then this will tell us that we don't lose any data by using this guy. So I stream music. So a lot of music is 12 bits, maybe even 8 bits audio from Spotify. Spotify is actually moving to 16 bits this year, which is going to be something. I know. If you like audio, then maybe this product's for you, and maybe your Spotify will sound worse because of this. But that's a good sign, for sure. But if you're not Spotify in 2022, then you're never going to tell that your signal got worse. You're never going to tell that your audio got worse using this amplifier, which is great. And besides that, I get kind of frustrated with doing circuits. I breadboard all this kind of stuff. And so I like something that looks like this. And so what we're going to use is a printed circuit board. Printed circuit board makes mechanical support for electrical connections. And so you see here there's like fiberglass, and then your copper. And then all you're going to do is it holds all of your copper together. And so you can put your components together like something like this. So this is a render of the board you have in front of you. And I've made some mistakes on it, I'll admit. But the good news is that this one is the finished product. And so if you want to buy any of them, then yours will actually work right, which is great. Here's the tool that shows all of the layers that the wires are. So the red ones on the top, green ones are on the bottom, very sparingly so you can see everything that's there. And then this is the circuit itself. So again, you have your audio jack at the input from your computer, the audio jack at the output to your headphones. You have the AC coupling, the amplifier, and then the driver, the common collector. And then this circuit down here is what's called a load dropout regulator. So this regulator just basically says, I have some voltage in the input, and I really want always to have the same voltage at the output. So the good news here is that I have a connector on there for 12 volts. And if you connect that 12 volt connector there, then it's always going to give you 5, and your amplifier will always have 5 volts. Super steady, helps get rid of the noise from the supply, more power supply rejection from that other graph, and hopefully it'll always work. All right, any questions? So this amplifier, I don't have any extras on me now. I have more boards, but no more pieces. It's going to be $6. We'll set up a Venmo, or cash is always king. All right, thank you all much. Yeah. So if anybody wants to come up here, I don't have headphones, but you're more than welcome to use your headphones with this. And you can hear how it amplifies.
Hey, the thing is,